Section: Introduction. In this section, we discuss the rise of large language models, LLMs, as powerful tools that can process vast amounts of internet data. These models serve as the backbone for many conversational agents that people use for gathering information and making decisions. Their natural language interface makes them more user-friendly compared to previous machine learning models. However, this widespread use brings up concerns about the accuracy and reliability of their predictions. Even though LLMs excel in various natural language processing tasks, they sometimes generate incorrect answers, particularly for questions outside their training scope. This is problematic because the models do not indicate uncertainty in their responses, which can mislead users into thinking their answers are always correct. This lack of clarity limits the model's usefulness in critical fields like medicine and law, where reliable information is essential. To address this, we explore how to enhance an LLM's predictions with expressions of uncertainty. These expressions would indicate how likely the model's predictions are to be correct, based on similar cases. For example, if a model says, "It is unlikely," and this corresponds to a 30% confidence level, we expect about 30% of those predictions to be accurate. Our goal is to ensure that these uncertainty-augmented responses are well calibrated. Previous methods have often avoided answering uncertain questions, but we aim to always provide an answer while clearly communicating the associated uncertainty. This approach allows users to decide whether to trust the model's information, seek further clarification, or look for additional sources. We believe that expressing uncertainty in words is often more effective than using numbers, as phrases like "I am certain" are easier for people to understand than percentages. Additionally, linguistic expressions can better convey the source of uncertainty and are more adaptable for various applications, such as text-to-speech. We focus on supervised fine-tuning with curated datasets to teach models how to express uncertainty in their predictions. We first evaluate the model's confidence by determining if each prediction is true or false, with confidence represented as a normalized probability for the true outcome. Our findings show that this self-evaluation is generally well calibrated for single-claim answers across different pre-trained models. By applying simple post-processing techniques, we can achieve excellent calibration for both base and instruction-tuned models. Next, we map confidence scores to linguistic expressions based on a framework developed from a survey that linked probability ranges to different uncertainty phrases. These expressions are then paired with the corresponding predictions to create a fine-tuning dataset. When we fine-tune the models on this dataset, they produce predictions with well-calibrated expressions of uncertainty. Our contributions include providing a fine-tuning recipe for adding linguistic expressions of uncertainty to models. We present calibration results for various model sizes after pre-training and alignment on 3 question and answer datasets. We find that pre-trained models are generally better calibrated than those fine-tuned for alignment, and larger models tend to have improved calibration. We also explore different methods for incorporating linguistic uncertainty into predictions. Our results indicate that fine-tuning with uncertainty expressions added after the actual answer yields the best calibrated models. In the related work section, we note that there has been extensive research on how machine learning models express uncertainty. We focus specifically on epistemic uncertainty, which arises from the model's lack of knowledge. Previous studies have examined how language models assess the confidence of their predictions, both in domain and out of domain. We build on these studies by using few-shot prompting to gauge the model's confidence in its outputs. Our work differs from others in that we obtain uncertainty targets in a pointwise manner, while some assign targets based on average performance across similar questions. We also investigate how the placement of uncertainty estimates affects their quality. Other researchers have worked on having models express uncertainty linguistically, but their methods often involve separate calibration steps. Our approach is more integrated, focusing on generating calibrated long-form predictions while also considering the position of uncertainty estimates relative to the answers. Section Summary. In this section, we discuss the development of large language models, LLMs, as accessible tools for information seeking, while highlighting their tendency to produce confident yet incorrect predictions, particularly in safety-critical applications. We propose a method to augment LLM predictions with linguistic expressions of uncertainty, enabling users to better gauge the reliability of the information provided, and outline our approach for fine-tuning models to achieve well-calibrated uncertainty expressions. Section: Setup and Method. In this section, we explore the question answering task where we utilize the Gemini 1.0 language model to express uncertainty in its answers. We work with a dataset made up of pairs of questions and their corresponding correct answers. We denote the questions as a set and the answers as another set. For any given question, the model generates a predicted answer through a specific decoding process. We divide our dataset into three distinct parts: few-shot, calibration, and training. Each part serves a different purpose in refining the model. The few-shot subset helps us assess the model's confidence in its predictions. The calibration subset is used to adjust the confidence scores, and the training subset is for fine-tuning the model. We also keep a separate part of the dataset for evaluation. To improve how models express uncertainty, we consider using few-shot prompting with examples that include uncertainty. However, we find that language models often struggle to produce well-calibrated expressions of uncertainty through this method. Additionally, this approach can be slow because it requires processing prompts for each question. To overcome these challenges, we look into supervised fine-tuning on datasets that include uncertainty expressions. A key factor in creating these datasets is ensuring that the uncertainty markers match the model's understanding of the questions. If the uncertainty expressions are inconsistent during fine-tuning, it can lead to incorrect outputs later. To maintain consistency, we first evaluate the model's confidence in its predictions using a true-false self-assessment task. With these confidence scores, we apply a technique called isotonic regression to calibrate the uncertainty estimates accurately. We then translate these calibrated scores into understandable expressions of uncertainty based on how humans perceive uncertainty. Next, we integrate these uncertainty expressions with the model's predictions in three different ways: placing the expression before the prediction, after it, or within it. After curating our dataset, we fine-tune the model to generate these expressions effectively. For evaluation, we measure the accuracy of the model's predictions by comparing them to the correct answers. We also assess how well the confidence scores align with the actual accuracy by plotting calibration charts. To summarize the calibration performance, we calculate two metrics: expected calibration error, which looks at the average difference between confidence and accuracy, and Breyer score, which measures the error between confidence and correctness across examples. Lower scores indicate better performance. Once we have fine-tuned the model to express uncertainty, we test its calibration on separate test sets. We extract the uncertainty expressions from the predictions and convert them into probability estimates. We then evaluate the calibration using the same metrics as before and plot the results. The entire evaluation process is detailed in our figures and algorithms. Section Summary. In this section, we investigate how to enhance the question answering capabilities of the Gemini 1.0 LLM by incorporating expressions of uncertainty through supervised fine-tuning on specially curated datasets. We outline our methodology for generating and calibrating uncertainty expressions, integrating them with model predictions, and evaluating the model's performance using metrics like expected calibration error and Breyer score. Section: Experiments. In this section, we describe our experiments and the datasets we used. We utilized standard question and answer datasets: Trivia QA, Ambit QA, and Truthful QA. For Trivia QA, we selected the Wikipedia version and took 16 examples for our few-shot dataset, 2,000 for our calibration dataset, and the rest for our training dataset. The test set was derived from the development set. In Ambit QA, we focused on the unambiguous set to address epistemic uncertainty, taking 16 examples for few-shot, 1,000 for calibration, and the rest for training, with the test set coming from the validation set. For Truthful QA, we divided the validation set into a few-shot dataset of 8 examples, a calibration dataset of 100, a test set of 100, and a training set of about 600. We considered a prediction correct if the language model evaluation judged it similar to any correct answers. We assessed the accuracy of various prompts on a uniformly sampled subset and manually verified their performance on smaller data subsets, finding that all tasks achieved over 95% accuracy. We conducted our experiments using the Gemini 1.0 model family, specifically 2 variants called small and medium, which differ in architecture size. Our study included both pre-trained and post-trained models, with the latter marked as IT. For fine-tuning, we generated 4 model samples for each question with a temperature setting of 1.0. We maintained balance in our curated dataset by limiting the number of examples per probability bin. Although our datasets included model-generated samples with probability expressions, we found that filtering based on correctness did not significantly affect performance, so we did not apply this filtering in our experiments. We trained with a batch size of 32 for 3 epochs, using the Atom optimizer with a cosine learning rate schedule, starting with a learning rate that increased to 5 times 10 to the power of -7 and then decreased to 5 times 10 to the power of -8. We then examined the calibration of the Gemini models on self-evaluation tasks, noting that the base models showed good calibration on trivia QA. Calibration improved with larger models, and pre-trained models outperformed instruction-tuned ones, consistent with existing literature. Post-processing confidence scores with isotonic regression significantly enhanced calibration. However, the Gemini models did not perform well on truthful QA, and despite some improvement from post-processing, it was not enough for effective dataset curation, leading us to exclude truthful QA from our fine-tuning. Next, we assessed the calibration of uncertainty expressions in our fine-tuned models on held-out test sets. The results indicated that these models produced well-calibrated expressions of uncertainty, consistent across different model sizes and types. Finally, we compared various methods for augmenting model predictions with uncertainty expressions, prefixed, postfixed, and interleaved. Our findings showed that postfixed uncertainty expressions, added after the main answer, resulted in the lowest calibration error. We believe this method simplifies fine-tuning since the uncertainty expression does not affect the main answer's sampling during decoding. In contrast, prefixed or interleaved expressions can influence the answer's sampling distribution, leading to poorer calibration.